So thanks so much for inviting us to share in this. It's been a great lineup, and we're honored to be included as part of this. I hope that what we have to share will sort of tie in some of these concepts. Many of you may already know that over the past couple of years, the OPG's been developing and conducting a series of proof of concept experiments, essentially, to demonstrate the benefits of skillful mesoanalysis in the field. And we've so far focused on the convective kinds of events. And so those experiments or those workshops have come to be known colloquially as Mesoanalyst Boot Camp. And the primary objective of these experiments was really just to reinvigorate the role of expert mesoanalysis as a science-oriented practice that can be aimed at delivering very precise tactical IDSS. So, that whole idea is certainly consistent with the goal of transitioning away from a product-centric sort of operating model toward one that's focused on the aspect of the facets framework that's focused on the area of disseminating a continual flow of information during high impact events. So today, Matt and I want to illustrate some of the techniques that are being taught and practiced during those experiments in hopes that maybe if you're not already doing so, you might be motivated to think how best to start integrating those kinds of concepts into your operations. And if time permits, I have noticed especially in Twitter, that there have been some folks being very innovative about trying to provide some assistance in that way, even remotely, because of the restrictions of the COVID-19 pandemic. So maybe we could even gather some of your thoughts about how you're applying those in a very innovative way to sort of keep your team apprised of how the environment is evolving with high impact convective events. So we often get the question about, just fundamentally, what do we mean? And when we're focusing on mesoanalysis, and of course, it's not just hand analysis. I am a big proponent of that. Matt is not so much. And so it's not about that specifically. It's really about exploiting the availability of many high resolution data sets that are now available to you in near real time, and finding a way to sort of diagnose which data are of primary importance and fuse those data together to provide you some intelligence. So we thought the best way to illustrate a few of the applications that we have in mind might be to take a look at a specific case and demonstrate some ways that a forecaster might, through careful observational analysis, infer some important details about how the environment is evolving, and then connect those insights to anticipating the development of severe weather hazards. And then, of course, as I mentioned, we want to bridge science and services. So the final step would be communicating those threats in tactical IDSS messaging. So with that in mind, we've selected this case from July 19th of 2018. It's relevant to a number of different mesoanalysis challenges, including predicting CI and diagnosing convective mode and convective mode transition, and the application of GOES 16 RGBs, so as well as GLM and terrestrial lightning data, as Chad alluded to. So for the first part, we're going to focus on Iowa, where the SPC had identified a slight risk of severe thunderstorms based on a 15% probability of damaging wind and large hail, with a 2% probability of tornadoes. So that's the sort of backdrop, and then I'll turn it over to Matt, and he can discuss that particular scenario in further detail. Matt?
Yeah, it helps if I unmute my phone. You can't have a weather service conference call or presentation without somebody talking on mute, so I filled that role today. So I appreciate getting the opportunity to do this. We put together this 4-panel D2D display that you see now, just to give you some kind of synoptic scale frame of reference for what was going on this day. It was an unseasonably dynamic setup with a 90-knot jet digging into the backside of a negatively tilted shortwave over the upper plains. And while northern Iowa is kind of getting onto the backside of that trough, and that's not typically the best place to look for forcing for ascent, there was some evidence that there was some of that forcing on the nose of that jet streak. This anomalously strong flow also contributed to unusually robust deep layer shear for July. And as shown in the upper right panel, there was a 500 millibar low moving across southern Minnesota, while at the lower levels, which are shown in the bottom right two panels, there was modest flow at 850 with south to southwest winds, maybe 20 to 25 knots from Iowa, northern Missouri up through Iowa and into southern Minnesota. And then at the surface, there was a kind of weak reflection of that upper level shortwave with a surface low there in southwest Minnesota and a surface boundary, as it were, extending kind of down along the Missouri River Valley and then curving back along the Kansas-Nebraska border. As might be expected for the middle of July, there was also an expansive area of warm, moist air covering most of the central and northern plains with surface dew points ranging from the mid-60s to the mid-70s. So on the next slide, we took a look at the 12Z sounding from Omaha, and it shows a pretty moist and unstable surface conditions, but the moisture is really shallow. And further, just above the surface, the flow is dominated by west to northwest winds on the backside of that shortwave. So it looks like this sounding is probably too far west to be representative of the conditions in our target area. Then if we look at the next sounding off to the east, that would be Davenport. There's more moisture available, certainly, than on the Omaha sounding, and that's leading to some very modest lapse rates aloft. Also, the flow at Davenport is really weak through all levels, and that indicates that this sounding is too far east really to be of interest. So our best proxy in this situation would be to grab a RAP analysis sounding near our area of interest. And that's what we're looking at here. We did we dropped a point near Des Moines and got a RAP analysis sounding at 17Z, and it paints a much different picture than either of the two observed soundings. The boundary layer is already quite unstable with ML Cape in excess of 1,700 joules per kilogram, and the effective inflow layer is nearly 1.5 kilometers, which is fairly deep, so early in the day. Low-level flow is pretty modest, as we noted earlier, but there is considerable veering in direction if you look at the hodograph, and that gives us an effective storm relative helicity of more than 200 meters squared per second squared. So next we put in a red visible mesoscale sector animation, and I know on the webinar this might not come through all that well. I do have these animations available as MP4s if anybody wants to really look at it in detail, because there are a number of key features showing up in this animation. That surface boundary I mentioned earlier is clearly visible to the west and northwest of Des Moines, with some convection. What happened to our presentation there, Kim? Oh, there we go. Some convection is already forming along that boundary up in northern Iowa. Also, if you look just west of Des Moines, there are some attempts at convective initiation in the moist sector ahead of that boundary, but the tops are being orphaned, indicating there's probably some capping in place, but that capping will be weakening due to evaporative cooling from the orphaning process. Now, if we look near and to the east of Des Moines, there's a broad area of stable billow clouds where the sheltered boundary layer is recovering from some earlier convection. And if you look closely in this area, you can observe the presence of some of these billow clouds at differing heights, that are nearly perpendicular to each other. Now, this crisscrossing of the stable billow clouds, and remember that the stable billow clouds are oriented perpendicular to the shear vector in that layer. This is a clear indication of a turning of the shear vector with height, which implies the presence of a rich reservoir of low-level helicity if that air were to be ingested into an updraft through surface-based effective inflow. And you might even be able to make an additional leap and think, perhaps there's even more helicity than what was being reflected on that 17Z RAP analysis sounding. And indeed, the 0Z Davenport sounding, which we're looking at now, reflected that concern. We had a very deep surface-based effective inflow layer of 2,700 meters, and the effective helicity in that layer is in excess of 300 meters squared per second squared. So by synthesizing these insights derived from our mesoanalysis, we can identify a threat area limited to about a dozen counties. The advancing surface boundary, where the viz image depicts agitated cumulus towers, forms the western limit to our threat area. Cooler temperatures, coupled with the laminar character of the low clouds over the eastern third of Iowa, indicate more stable air that should bound the eastern edge of the threat. To the south is an area of clearing associated with convectively processed air resulting from some earlier storms over northern Missouri. While the air mass there down to the south could certainly recover sufficiently to support convective hazards with time, at least for the next few hours, it's safe to assume that there is no significant threat of surface-based effective inflow from this region. There is some uncertainty as to the southwest extent of the threat, and you can see some open cell cumulus forming in that area, but the advancing boundary from the northwest should narrow that corridor quickly. So if we account for some eastward progression of the surface convergence zone prior to the onset of severe weather, that leaves us with an enhanced threat for severe weather that encompasses an area that looks something like this. So we now need to focus our attention on predicting storm mode and identifying associated hazards. We have seen some indication that there is a potential for rotating updrafts, but we need to determine if storms can remain discrete long enough to pose an appreciable tornado threat. As a reminder, there are three primary factors that drive the likelihood of achieving a persistent discrete convective mode. Assuming first that updrafts have sufficient residence time in a region of moist, unstable, surface-based effective inflow layer air, the three drivers in order of importance are boundary relative storm motion directed off of the initiating boundary, the orientation of the deep layer shear to the initiating boundary, and storm relative anvil level flow. To assist us with this type of diagnostic, we put together a zip file containing numerous D2D bundles, which were developed for use by Mesoanalyst bootcamp participants. One of the most frequently used bundles is the one you see on the screen now. This procedure was designed to aid in diagnosing the potential for convective initiation via the left two panels showing fields related to forcing, the availability of unstable surface-based parcels using surface-based CAPE in the bottom right, and the potential for the formation of discrete storms by analyzing a number of vector products in the upper right. And all of those vectors go to, they work with those three factors of primary importance for determining if storms can remain discrete. So if we zoom in on that upper right panel, we can clearly see the roughly northwest or northeast to southwest orientation of that advancing boundary reflected in the CAPE image. The 700 to 300 millibar mean wind is shown by the black vectors, and that's used as a first guess for storm motion. Deep layer shear is indicated by the light blue wind bars. Both of these vectors have a strong component orthogonal to that initiating boundary. In addition, the magnitude of the bulk shear, which is 40 to 50 knots over central and southern Iowa, would certainly be supportive of supercells. So then on the next slide, we added in these yellow arrows, which we previously toggled off just for clarity. And they depict the 200 to 300 millibar storm relative wind vectors. And this is a good proxy for the orientation of anvil plumes. This flow too is oriented orthogonal to the initiating boundary, although it's not very strong. Taking all these factors into account, there does appear to be a significant threat for discrete storms with rotating updrafts. Moreover, the presence of strong 0 to 1 kilometer helicity, which is shown in the magenta contours, which was previously implied by those crisscrossing billow clouds, suggests an elevated potential for tornadic supercells. And that potential did in fact come to pass with the formation of 2 EF3 tornadoes in south central Iowa. Having clearly delineated our tactical threat area and the potential hazards, we are now prepared to communicate useful information to decision makers. Before doing that, we would obviously want to ensure that all the members of our internal warning team are on the same page. Next, it would probably be prudent to hold a brief coordination call with SPC just to notify them of your intent to convey a short-term conditional threat of significant tornadoes in a very focused area of central Iowa. After that, you or your DSS forecaster could create and disseminate your expectations to emergency managers and other core partners via chat, briefings, or sit-reps. This clears the way to then address the public using clear, concise, actionable information crafted in a social media graphic. And finally, we advocate outlining your reasoning in a mesoscale AFD update. This serves to document your science-based thinking, and it earns credibility with users that the Weather Service is a trusted source of meteorological expertise. And we had an emergency manager in attendance at our Mesoanalyst boot camp, and he reiterated this point to the participants that the expertise related in that AFD increases his confidence that we know what we're talking about and we can be trusted. So that wraps up this section of the presentation. I'll turn it back over to Kim for the next section.
Okay, very good. Thanks, Matt. So that first portion of our sort of 3-part July 19th review focused on identifying storm mode and associated hazards and isolating the major threat area. So let's take a look now at a situation where the challenge is related more to diagnosing a potential mode transition. So we're going to turn our attention to Kansas. And you'll recall from Matt's first slide regarding the synoptic scale setup, there was a strong jet streak digging into the base of that shortwave over the northern plains. That jet streak is pretty clearly evident in this water vapor animation, along with some developing convection near and really just south of the Kansas-Nebraska border. So if we zoom in on that area and add some isentropic analysis fields, we can see that this elevated convection is being driven, at least in part, by warm advection lift and associated isentropic upglide implied by that in this sort of moderate west-northwest flow. And it's also evident that very steep mid-level lapse rates off the elevated terrain are being advected eastward toward the central plains. So if we shift our attention to visible satellite imagery, this is taken at 16Z. It shows the updrafts of the elevated convection oriented sort of northwest to southeast and kind of along the mid-level thermal gradient there. And surface observations depict this relatively broad zone of confluence associated with an east-west boundary out across northern Kansas with temperatures south of the boundary in the 90s and dew points in the 70s. And really even behind that wind shift line, I mean, the air over southern Nebraska is very warm and humid. So the 12Z sounding from North Platte depicts a very shallow near surface moisture layer that is trapped beneath a strong inversion. So this is the area just north of that boundary. And then that is surmounted by that deep elevated mixed layer with lapse rates greater than 8 degrees C per kilometer. Now contrast the North Platte sounding with the 12Z sounding in northeastern Kansas from Topeka. Topeka's observation shows much deeper moisture, somewhat more stable mid-levels with an observed lapse rate of 6.9 degrees C per kilometer in that steepest lapse rate area identified by the yellow bar. That's a little bit more than moist adiabatic. However, as I alluded to a moment ago, given that flow pattern, we can reasonably expect lapse rates over northeast Kansas to steepen as that elevated mixed layer advects into the area over the next few hours. And fortunately for us, Topeka took a special 18Z sounding on that day. So we can note the observed changes over that 6-hour period, and that certainly verifies the presumption. Mid-level lapse rates here steepened by 18Z to about 8C per kilometer, with surface dew points in the 70s and mean mixing ratio of about 16 grams per kilogram. So if we factor in diabatic heating, that yields a very deep buoyant layer with CAPE somewhere in the 4,000 to 5,000 joules per kilogram range. So upshot of all that, buoyancy and shear considerations would certainly be supportive of supercells with lots of residence time in the moist sector. But sustaining discrete mode for storms is certainly questionable, given the translation speed of the outflow boundary where new updrafts are expected to begin to regenerate. I mean, overall, this setup would seem to be conducive for the amalgamation of cold pools and upscale growth into an MCS with damaging wind potential. Although maybe we couldn't rule out, a couple of discrete storms early on as the system is initially becoming surface-based and developing. So putting that scene in motion, and again, as Matt pointed out, I know the animations are a little kind of herky-jerky here, but we will provide these slides if you're interested, and you can see them in a little more fluidly. At any rate, you can see there is new vigorous convection, these convective towers associated with this cluster of storms are tracking east-southeast across northern Kansas. This animation goes right up to 18Z. It's really still not clear from the animation whether the updrafts are surface-based, although we would certainly get some confidence that if not, they soon would be based on that Topeka sounding. The orientation does still at this point appear to be largely northwest to southeast, and the lack of any cumulus over northeast Kansas, is evidence that would suggest boundary layer processes are not really involved in updraft production ahead of the advancing convection just yet. So the two big questions at this point are, will these storms become rooted at the surface as suggested by that sounding? And if they do, what will the evolution of the cluster look like? So one clue we might look for as an indication of transition, as we mentioned, the whole setup looks like it will be more favorable to becoming more of a QLCS kind of a system as the cold pools amalgamate, as what Ariel Cohen likes to say, as the spreading out of the pancake batter, sort of an analogy of the cold outflow. So that would suggest that we would start getting a realignment of cells to something more north-south as cold pools do amalgamate, because we'd expect new updrafts to begin developing on the leading edge of that outflow orientation as they ingest that high theta E air over northeast Kansas. So with anomalously strong west-northwest flow, as was pointed out earlier, as well as deep layer shear, that's quite strong, and forward propagating Corfiti vectors are on the order of like 30 to 40 knots out of the northwest. So we would expect a signal that that there's an acceleration in the propagation of the system as it organizes, amplified by then maybe internal feedback like development of a rear inflow jet, for example. And indeed, an animation of the GOES 16-day convection RGB illustrates that evolution did begin to happen very soon after 18Z and proceeding to almost 21Z in this animation. So the bright yellow cores, as a quick reminder, are associated with very small ice crystals being lofted rapidly to the tops of the clouds. So that correlates very well with especially vigorous updrafts. I mean, they're getting lofted rapidly because there's very little residence time in the updraft. So that orientation can be clearly seen to shift to a more generally north-south arc as the MCS begins to mature. And then that notable increase in bright cores coupled with the obvious bowing segment along the leading edge infers that the system is beginning to organize and intensify as well. And then in addition, you might note the new convection developing in the vicinity of the outflow boundary associated with that early morning convection over Missouri that Matt pointed out in the Iowa case. So cell mergers and boundary interactions appear to be imminent there, which would pose additional concerns, of course, about enhanced severe weather threats. So, I mean, you would verify all these observations with radar by this point, but a lot of information about the mesoscale environment can be deduced simply from careful analysis of satellite imagery and other observations. And then incidentally, this system did continue to grow upscale with some very interesting mesoscale evolution, and it was associated ultimately with several fatalities at Table Rock Lake that nationally got some attention as the so-called duck boat incident. So some very interesting lessons learned in terms of both science and service from the regional service assessment that Randy led. And so if you have not read that, I would recommend that to you. So for the final section of the three-part case study, I'll turn it back over to Matt to talk a little bit more about another RGB and lightning data.
Okay, thanks, Kim. And as Kim alluded to, we're going to take a look at some additional applications of one more GOES 16 RGB and lightning data. And for this, we're going to be kind of focusing in on that convection that we just saw on the day convection RGB developing near the Kansas City area. So for this section, we're going to be looking at the day cloud phase RGB, which we see here, and we have it paired with GLM. And we want to focus on the developing towers along that outflow boundary just to the east of the Kansas City metro area. The day cloud phase RGB gives us the ability to anticipate convective initiation and associated lightning activity by monitoring for very specific color changes in convective cloud tops. Now, just as a refresher about the day cloud phase RGB, it's comprised of the clean IR band in the red gun, red visible is in the green, and the 1.61 micron snow ice band is in the blue. And the snow ice band is really key here because it's really reflective for liquid water, but not for snow and ice. And it's that change that's going to give us our signals here. So warm liquid clouds like those up near the Missouri-Iowa border will show up light blue. But as the depth of the convective tower increases and ice crystals begin to form, the contribution from the snow ice band in the blue gun drops, leading to an increasingly green appearance to the cloud top. Once a convective tower has a considerable amount of green and eventually moving into some yellowish shades, lightning activity is becoming imminent. We can use this insight to inform outdoor events of the hazard so they can take necessary precautions to protect lives. In this particular case, in-cloud lightning was detected less than 5 minutes after the end of this loop, and the first cloud-to-ground lightning followed shortly thereafter. So I didn't put together, actually Chad put together, and I just stole it from him. So we have a graph here showing how the day cloud phase RGB changes over time with a maturing convective cloud top. Now, this graph isn't from the Kansas City case. I think it's actually from Florida, but it's illustrative all the same. The green contribution from the red visible is always quite high. As you can see, it's up in the 90 to 100% range pretty much constantly. The blue contribution starts off rather high when the cloud is all liquid, but then it drops rapidly just after 17Z there as ice crystals begin to be lofted to the cloud top. Now, conversely, the red contribution from the clean IR starts low when the cloud top is relatively warm, but increases quickly as the cloud top increases in height and cools. The dotted line that's shown there is the MRMS reflectivity at minus 10C. And this is important to include here because we don't want to come to rely on any single tool, but rather we want to use multiple data sets that are supportive of each other to gain the most insight that can be translated into actionable information for decision makers. So in this case, having a display with the day cloud phase RGB, your lightning data, and the minus 10C MRMS reflectivity is really great if you're working a lightning safety situation. Now, the light gray bar over to the right shows the time of the first in-cloud lightning, and then the black bar almost all the way to the right shows the time of the first CG. So we can see here by carefully monitoring the day cloud phase and the MRMS minus 10C reflectivity in conjunction, it's possible to give decision makers 10 minutes or more lead time of potential lightning activity. So now we've advanced the clock about 30 minutes, and clearly we have convective initiation east of Kansas City. We're going to take a look now at an application of lightning data as it pertains to updraft strength. In this animation, and I hope it comes through relatively well on the webinar, we have both GLM and Earth Networks lightning overlaid with the day cloud phase RGB. It's important to note here that we always recommend pairing GLM with terrestrial lightning detection. Each of these sensors has their own strengths and weaknesses, but together they're very complementary. Using the two different sensors together increases the likelihood of detecting any given lightning strike. By using the GLM, we get a really good representation of aerial coverage, and the Earth Networks gives us lightning detection without any parallax. So you can see how they work together to give us a more total picture of the lightning activity. So if we look at that newly developed storm just east of Kansas City there, when the updraft is strong, like here where it's newly formed, the mixed phase collisions that lead to the charge separation that in turn cause lightning are very tightly concentrated within the updraft. Then, as the updraft weakens with time, the grapple and ice crystals are able to spread down shear. And we can observe this phenomena in the terrestrial-based point lightning data. So next we have a still image that was captured shortly after CI with the convective activity there again just to the east of Kansas City. And you can see in this image that the lightning strikes are very tightly clustered together. Then if we compare that with the image in the next slide, which was captured just 14 minutes later, it shows the lightning activity that's spreading out down shear, indicating that that particular updraft has weakened some. So this information could be useful to gain insight as to how updrafts are cycling over time. So why is all this important? If we take a look at this graph, which shows in-cloud lightning and cloud-to-ground lightning activity versus time leading up to tornado genesis, with the tornado genesis being indicated by the vertical dot dash line there at t equals 0, note the large rapid increase in the in-cloud lightning activity, while there was almost no change in the cloud-to-ground lightning activity. This is why it's always important to pair GLM with ground-based lightning data. GLM, being a color-enhanced image, can alert us quickly to a lightning jump. It grabs the eye very quickly. And then the terrestrial data can tell us what type of lightning is causing the jump. And a very large jump in in-cloud lightning could be a signal of a rapidly strengthening updraft. And this leads us to one final important point on this topic, and this was given to me by Chad shortly before we did this presentation last week. And we're working remotely, I couldn't update the AWIPS imagery. So previously on that slide, we were looking at the day cloud phase along with the GLM and all of the Earth network strikes, both in cloud and cloud to ground. If your job is monitoring overall convective trends in support of warning operation, the only type of lightning you should have loaded from the terrestrial source is cloud flashes. As this graph clearly shows, increasing updraft speed will be reflected in cloud flashes and not CGs. So, obviously having CGs loaded is important for, lightning safety support, but when diagnosing updraft strength, they're really just noise on your display. So it's best to unload them in that situation. So we have one little bonus section here that I'm going to turn it over to Kim to cover from our Mesoanalyst Bootcamp.
Okay, very good. Thanks, Matt. And just another minute and a half or so. We're just going to shift gears, and we just wanted to talk very briefly about another area we explored during the boot camps, and that is how we can begin to think about exploring probabilistic space and then using that information to shape our messaging with tools like ensemble situation awareness tools, with tools like Scram that's statistical but very strong probabilistic base, with NBM viewer and more of those kinds of things coming online, even SIPS analog kinds of products. There are lots of opportunities for us to shape our messaging and to sort of provide some nuance to the potential for threats. And so this quick example, without providing a lot of background on the situation, from a different day in July 2018, there were two marginal risk areas, one in the desert Southwest, one in the northern high plains. And so let's take a look at conceptually a probability density function for each of those areas. So if we look at the PDF for the Arizona risk area, it's very narrow and steep with respect to probability of occurrence and how severe the hazard is going to be. It's basically a traditional sort of July threat in Arizona, marginally severe downburst winds as storms come off the Mogollon Rim and down into the lower deserts where there's higher Cape air to ingest. So there's really little to no chance of higher end threats. But compare that with the initial PDF for the Northern Plains. So that area has a much more conditional threat. The kinematic fields and the buoyancy, there's a broader range of possible outcomes, including at least a small risk of some more impactful hazards, as indicated by the long right-hand tail. So if we move later in time, without knowing the details, just take my word for it, it became clear that the conditional risk of supercell development was becoming increasingly likely. So that also meant attendant hazards may even include some discrete supercells with tornadoes. And so accordingly, the PDF itself shifted to the right. And using that kind of information, even if it's sort of only a mental visualization tool, it can help you sort of get your arms around the envelope of possibilities and help to drive an office's messaging and relate reasonable worst case scenarios to court partners, as well as what is most likely to occur. And if things go off the rails, in what direction might they go? So that can certainly be useful. And I think there's some opportunities for you to start thinking about incorporating probabilistic space in your own messaging, even for convective hazards. So again, benefits of skillful mesoanalysis, I think, are very clear. Many of you are already applying them, and so we certainly applaud that. it helps us to improve our tactical IDSS, providing precise, actionable information to partners, as we've alluded to in all three of the sections of this single July 19th event, and especially in the area where there are information gaps between outlook, watch, and warning in the spirit of the facets framework. So I think by having a higher understanding of mesoscale meteorology, WFO forecasters are better equipped to interact with and collaborate with SPC. They desire that. A common criticism among field forecasters we have heard on a number of occasions is concern that the recent focus on IDSS dilutes the science in our mission. But I think that these kinds of examples provide unequivocal proof that there's still plenty of deep science to be undertaken in an IDSS world. So hopefully we also at least open the door to begin having you think about exploiting probabilistic space to craft messaging and drive better risk management decisions. So in the interest of time, I'll just leave these key takeaways on the screen. These are quotes directly from participants' end of week surveys from the Mesoanalysis workshops, and leave them there for you to read. And maybe we have a couple of minutes to take any questions.